Welcome to an introduction to vector-valued functions, matrix-valued functions, and also writing a system of ordinary differential equations using matrix notation. A vector-valued function is a vector whose entries depend on some variable. A matrix-valued function is a matrix whose entries depend on some variable. So if t is the independent variable, we write a vector-valued function as x of t equals a vector expresses a column matrix where each entry is a function of t. Similarly, a matrix-valued function expressed as a of t is equal to a matrix where each entry is a function of t. Notice how we can view a vector-valued function as a special matrix-valued function, except recall each column matrix does represent a vector. To find the derivative of x prime of t, which is the derivative of the vector-valued function, we simply differentiate each entry with respect to t. Similarly, to find the derivative of a matrix-valued function a prime of t, we differentiate each entry with respect to t. The rules of differentiation for matrix-valued functions are similar to the rules for normal functions. If we let a of t and b of t be matrix-valued functions, little c be a scalar, and big C be a constant matrix, we have the following differentiation rules. The derivative of a of t plus b of t equals a prime of t plus b prime of t. The derivative of a of t times b of t is equal to a prime of t times b of t plus a of t times b prime of t. This should remind us of the product rule of differentiation. Next, we have the derivative of little c times a of t equals little c times a prime of t. And then we have the derivative of big C times a of t equals big C times a prime of t. And similarly, the derivative of a of t times big C equals a prime of t times big C. Recall that small c is a scalar and big C is a constant matrix. And now let's talk about systems of ordinary differential equations. A first-order linear system of ordinary differential equations is a system that can be written as the vector equation shown below, where we have x prime of t equals p of t times x of t plus f of t. So again, if we can write it in this form, it is a first-order linear system of ordinary differential equations, where p of t is a matrix-valued function and x of t and f of t are vector-valued functions. We will often suppress the dependence on t and write the vector equation in the simpler form shown here. X prime equals p times x plus f. A solution of the system is a vector-valued function x satisfying the vector equation. And now let's practice writing a system of ordinary differential equations using matrix notation. Let's write the given system of equations using matrix notation. We have x1 prime equals 2t times x1 plus e to the t times x2 plus t squared, and then we have x2 prime equals x1 divided by t minus x2 plus e to the t. To begin, we write x1 prime and x2 prime as a 2x1 column matrix, which represents a vector-valued function. And then on the right side of the equation, we want p of t, which is a matrix-valued function, times x of t, which is a vector-valued function, plus f of t, which is another vector-valued function. P of t is going to contain the functions of t being multiplied by, in this case, x1 and x2, and f of t is going to be the vector-valued function only containing the functions of t. So analyzing the right side of the first equation, notice we have 2t times x1 plus e to the t times x2, and then plus t squared. And then on the right side of the second equation, we have x1 divided by t, which we can think of as 1 divided by t times x1 minus 1 times x2 plus e to the t. This indicates p of t is going to be a 2x2 matrix-valued function, where the first row is 2t and e to the t, and the second row is 1 over t and negative 1. And then we have times the vector-valued function x of t, which has components x1 and x2, expresses a 2x1 column matrix, and then we have plus the vector-valued function f of t, which are the terms in the two equations that are only functions of t, giving us entries t squared and e to the t. From here, we often replace the vector-valued function with entries x1 prime and x2 prime with x prime or x prime of t, and we also replace the vector-valued function with components x1 and x2 with just vector x. We will mostly concentrate on equations that are not just linear, but are in fact constant coefficient equations. That is, the matrix P will be constant, it will not depend on t. When the vector valued function f is equal to the 0 vector, we say the system is homogeneous. For homogeneous linear systems, we have the principle of superposition, just like for single homogeneous equations. And we'll talk more about this in the next lesson. I hope you found this helpful.